Welcome to Applied Programming, a full stack development experience, lecture 9, where we have testing and security. We will start with a short overview and then we will talk about testing. We will also have a hands-on part about testing and then we will talk about security. Let's start with a very quick overview. So, in the very early parts of the lecture, we looked into things like the overall course, and then the processes and the database, and then the backend. And it was, let's say, less than 50% of the course. So a bigger part has been the front end, which I had this analogy. It's like Brave New World, as it's different to what you have learned in the previous semester. If we look at the topics, last time we talked about the user interface with Angular material, and this time it's also about product development, so not necessarily just Angular, but also relates to backend. Testing techniques for full stack web applications. We are going to explore one of the most critical aspects of software development, testing. I know many of you have business backgrounds and you might wonder why we dedicate a lecture to testing. Here's the reality. In the business world, a bug in production can cost thousands or even millions of dollars, damage your company's reputation, and erode customer trust. Testing is essentially quality assurance for software. It's like having multiple checkpoints before a product reaches the market. Think of testing like this. If you were launching a new product in the physical world, you wouldn't ship it to customers without checking that it works, right? Software is no different. However, unlike physical products, where you can visually inspect quality, software behavior is complex and hidden. That's why we need systematic testing approaches. In this part of the course, we'll cover the fundamental testing techniques that you'll use in your full stack applications. We'll look at unit testing, integration testing, and end-to-end testing. By the end of this lecture, you'll understand what each type of test does, when to use it, and how to implement it in both your ASP.NET Core backend and Angular frontend. Don't worry, we'll keep everything practical and focused on what you actually need to build reliable applications. Let's start with the fundamental question. Why bother testing at all? From a business perspective, there are compelling reasons. First, catching bugs early is exponentially cheaper than fixing them later. Studies show that a bug found during development might cost $100 to fix, but the same bug found in production could cost $10,000 or more when you factor in emergency fixes, customer support, lost revenue, and reputation damage. Think about it. If you discover a calculation error in your pricing algorithm before launching the product, you can fix it in a minute. If customers discover it after they've been charged, you're dealing with refunds, legal issues, and angry customers on social media. Second, tests prevent regression. Regression means that when you add a new feature, you may accidentally break something that was working before. Imagine you are running an e-commerce site. You add a new discount feature and suddenly the checkout button stops working. Without tests, you might not notice until customers start complaining. With tests, you'd catch this immediately. Third, tests serve as living documentation. When a new developer joins your team, or when you return to your own code 6 months later, tests show exactly how the system is supposed to behave. They are like a specification that never gets outdated because if the test passes, the behavior is correct. Fourth, tests give you confidence to make changes. Without tests, every deployment is stressful. You're never quite sure if something will break. With good test coverage, you can deploy with confidence, knowing that if the tests pass, your application works. Finally, writing testable code forces you to write better code. Code that's easy to test tends to be more modular, less coupled, and better organized. It's a positive side effect of testing discipline. This pyramid is one of the most important concepts in testing strategy, and it's based on very practical business considerations: cost, speed, and reliability. At the bottom, we have unit tests. These should make up most of your tests. Unit tests are fast. For example, in milliseconds they run. They are cheap to run and test individual pieces of code in isolation. Think of them as testing individual Lego bricks to make sure each one is the right shape and color. In the middle, we have integration tests. They should be much less than the number of unit tests. These tests will test how different parts of your system work together. For example, does your API correctly save data to the database? These tests are slower and more complex because they involve multiple components. This is like testing how several Lego bricks connect together. At the top, we have end-to-end tests. These tests test the entire application from the user's perspective, including the user interface. They are slow. They may be running in minutes or even in hours. They are expensive to maintain and fragile. They break easily when you change the user interface. This is like testing an entire Lego model to see if it works as intended. Why this distribution? It's about efficiency. A unit test might run in 5 milliseconds and test one function. An end-to-end test might take much longer and test the same function as part of a larger workflow. If that end-to-end test fails, you have to debug through the entire stack to find the problem. If the unit test fails, you know exactly where the problem is. From a business perspective, this pyramid means you can run thousands of tests in seconds during development, getting immediate feedback. If you relied mainly on end-to-end tests, you would wait minutes or hours for feedback, dramatically slowing down development. The key insight: use the cheapest, fastest tests that can reliably catch the bug. Don't use an end-to-end test to verify that a mathematical calculation is correct. That's what unit tests are for. Unit testing, the foundation. Let's dive into unit testing, which is the foundation of our testing strategy. A unit typically means a single method or function, the smallest testable part of your application. The key principle of unit testing is isolation. You're testing one specific piece of logic without involving anything else. Think of it like testing a calculator. You want to verify that when you press 2 plus 2, you get 4. You don't need to involve the calculator's battery, circuit board, or display to test this logic. Why isolation? Two main reasons. First, speed. Isolated tests run in milliseconds because they are just executing code in memory. You can run thousands of these tests in seconds. Second, clarity. When a unit test fails, you know exactly which unit is broken. There is no detective work required. Let me give you a concrete business example. Imagine you're building an e-commerce system. You have a method that calculates the total price of an order. It takes the item prices, it applies discounts, it adds tax, and adds shipping. This is perfect for unit testing because you can test: does it correctly sum item prices? Does a 10% discount give the right result? Does it calculate tax correctly? What happens with zero items? What happens with negative prices, which is of course invalid input? Each of these is a separate unit test. You don't need to involve the database where the orders are stored. You don't need to involve the payment gateway or the user interface. You're just testing the calculation logic itself. Unit tests should be fast, focused, and independent. Fast means milliseconds. Focused means testing one specific behavior per test. Independent means tests can run in any order and don't affect each other. In the next slides, we'll see concrete examples in both C# and Angular. Now let's look at a concrete example in C#. We are using XUnit, which is one of the most popular testing frameworks for .NET. It's free, well documented, and integrates perfectly with Visual Studio. Let me walk you through this example step by step. First, we have our order service class with a calculate total method. This method takes a list of prices and a discount as a decimal where 0.1 means 10%. Calculates the subtotal, applies the discount, and returns the result. This is the code we want to test. This is our unit. Below that, you see the test method. Notice it has a fact attribute. This tells XUnit that this is a test method to run. The method name follows a convention. Method name underscore scenario underscore expected result. This makes it crystal clear what the test is checking. Here we are testing that calculate total when given a discount returns the correct amount. The test follows the AAA pattern: arrange, act, assert. This is a universal testing pattern you'll see everywhere. Arrange means set up everything you need for the test. Here we create an order service instance and prepare our test data, which is 3 prices totaling 60. Act means execute the code you are testing. Here we call calculate total with our prices and a 10% discount. Assert means verify the result is what you expected. We expect 54, which is 60 minus 10% of 60, which makes 60 minus 6, that is 54. From a business perspective, this test gives you confidence that your pricing logic is correct. If someone later modifies the calculate total method and breaks it, this test will immediately fail, preventing the bug from reaching production. One important note. Notice how we are testing actual business logic, not trivial things like getters and setters. Focus your unit tests on code that has complex behavior or is critical to your business. You typically have multiple tests for this method, one for no discount, one for 100% discount, one for an empty price list, etc. Each test focuses on one scenario. Let's look at the Angular side now. Angular uses Jasmine as its testing framework and Karma as its test runner. Don't worry about these names, they are just tools. Jasmine provides the testing structure and Karma runs the tests in a browser. The structure is very similar to our C# example, but with JavaScript, actually TypeScript syntax. Let me break this down. First, we have our calculator service with an add method, simple business logic that adds two numbers. This is our unit to test. Below, we have the test suite. The describe block creates a test suite, a group of related tests. Think of it as a container. Here we are grouping all tests for calculator service. The before each function runs before each test. This is where we do setup work. Here we create a fresh instance of calculator service before each test. Why fresh each time? To ensure tests are independent. One test doesn't affect another. The it block is an individual test, similar to fact in C#. The description should add two numbers correctly, clearly states what we are testing. Notice it reads like plain English. Jasmine is designed to be readable. Inside, we again follow AAA. Arrange to set up test data, act to call the method, and assert to check the result. The expect function with to be is Jasmine's assertion syntax. It's saying, I expect this result to be 8. From a practical standpoint, when would you use this in your Angular application? Let's say you're building a shopping cart in Angular. You might have a service that calculates totals, applies coupon codes, or manages cart state. These are all perfect candidates for unit testing. You don't need to render components or make API calls. You're just testing the business logic in your services. One tip for Angular testing. Focus your unit tests on services and business logic, not on component UI. We will handle UI testing differently, which we will see in integration and end-to-end testing. The same principles apply as in C#. Keep tests fast, isolated, and focused on one behavior. You should be able to run all your Angular unit tests in a few seconds. Now we need to address a practical challenge. What do you do when the code you're testing depends on something external like a database or a payment gateway? Let me paint a scenario. You're testing a service that processes orders. This service needs to save the order to the database, charge the customer's credit card, send a confirmation email. If you tried to unit test this service by actually hitting the database, charging real credit cards, and sending real emails, you would have massive problems. First of all, tests would be slow, because, for example, database operations take time. Also, tests would be unreliable. What if the database server is down? Tests would have side effects. You would clutter your database with test data. Tests would be expensive. You would actually charge credit cards perhaps. And tests couldn't run in parallel, because they would interfere with each other. This is where mocking comes in. A mock is a fake object that pretends to be the real thing, but is actually under your control. Think of it like a crash test dummy. It looks like a person and behaves like a person for the purposes of the test, but you're not putting a real person in danger. When you use a mock database, you're not actually connecting to a database. You're using a fake object that responds exactly how you tell it to. Want to test how your code handles a database error? Tell the mock to throw an error. Want to test successful saves? Tell the mock to return success. you have complete control. The key benefits from a business perspective. Speed. Tests runs in milliseconds, not seconds. Reliability. No external dependencies that can fail. Isolation. You're testing your logic, not the database vendor's logic. Safety. No risk of corrupting real data or charging real credit cards. Flexibility. You can simulate any scenario, even rare edge cases. Mocking is essential for true unit testing. Without mocking, you're not testing units in isolation. You're testing the entire system, which is actually integration testing, which we will cover shortly. Let's look at concrete examples of how to use mocks in both C# and Angular. This example demonstrates mocking in C# using mock, which is the most popular mocking library for .NET. Let me walk through this carefully because this concept is crucial for real-world testing. First, notice we define an interface email service. Interfaces are key to mocking. They define a contract without specifying implementation. In real code, you would have a concrete email service that actually sends emails via SMTP or an email API. But for testing, we will use a mock. Next, look at order processor. It receives an email service through its constructor. This is called dependency injection. Instead of order processor creating its own email service internally, which would tightly couple it, we pass the service in. This makes order processor testable because we can pass in either a real email service or a mock. When process order is called, it does whatever order processing logic you have, then calls the email service to send a confirmation. In production, this would send a real email. In testing, we will use a mock. Now the test. We create a mock of email service using new mock email service. This creates a fake email service that implements the interface but doesn't do anything unless we tell it to. We pass this mock to order processor via mock_email.object, which gives us the fake email service instance. We call process order with a test order. The method runs, and when it tries to send an email, it calls our mock instead of a real email service. The mock records that the call happened. Finally, we verify mock_email.verify. It checks that send email was called exactly once with the correct email address and subject. This is the assertion. We are not checking that an email was actually sent. We don't care about the email provider's implementation. We are checking that our order processor correctly tried to send an email with the right parameters. From a business perspective, this lets you test order processing logic without setting up an email server, sending thousands of test emails, dealing with email delivery issues, or waiting for network operations. You are testing your code. Does order processor call the email service correctly? The email service itself should have its own tests. This separation of concerns is what makes testing manageable at scale. Now we move up the testing pyramid to integration testing. While unit tests check individual pieces in isolation, integration tests check that multiple pieces work together correctly. Think of it this way. Imagine you're building a car. Unit tests verify that the engine works, the transmission works, and the brakes work, each of them independently. Integration tests verify that when you connect the engine to the transmission, they work together correctly. You can have a perfect engine and a perfect transmission, but if they don't fit together properly, the car won't move. In web applications, integration testing typically means testing things like: does your API correctly save data to the database? Does your authentication system work with the database? Do multiple services interact correctly? Does your API correctly consume an external API? And so on. Integration tests often use real dependencies. For example, you might use a real test database, not production of course, to verify that your data access code works. Or you might make real HTTP calls to your own API to verify endpoints work correctly. From a business perspective, integration tests catch a different class of bugs than unit tests. Here are real scenarios integration tests would catch. Scenario 1. Your unit tests verify that your order service correctly calculates totals and that your database repository correctly saves orders. But when you connect them, the order service passes a decimal and the database expects an integer. Your app crashes. Integration tests would catch this. Scenario 2. Your frontend correctly formats dates in US format, month, day, year, and your backend correctly parses dates. But your backend expects ISO format, year, month, day. In production, all date submissions fail. Integration tests between frontend and backend would also catch this. Scenario 3. Your code works perfectly with a test database on your machine, but the production database uses a different SQL dialect that doesn't support a specific query syntax. Integration tests with a production-like database would catch this. Integration tests are slower, perhaps seconds instead of milliseconds, because they involve real input-output operations, database queries, HTTP calls, file operations. They are also more complex to set up, because you need test databases, test configurations, etc. That's why we have fewer integration tests than unit tests. You use integration tests strategically for critical interaction points, while unit tests cover the individual logic. This is a real-world integration testing example for ASP.NET Core. It's more complex than unit testing, but let me break it down step by step. We are using Web Application Factory, which is a powerful tool that comes with ASP.NET Core. It creates an in-memory version of your entire web application for testing. Think of it like spinning up a complete, fully functional version of your API, but in memory rather than on a server. This is fantastic for integration testing because you're testing the real application stack. In the constructor, we create an HTTP client that can talk to this in-memory application. This client works exactly like a real HTTP client. You can make GET, POST, PUT, DELETE requests just like a real user or frontend would. Let's look at the first test. Get products, return success status code. This is testing your entire GET endpoint. The HTTP routing, for example, does API/products route correctly? The controller, for example, does the products controller handle the request? The service layer, does it retrieve products correctly? The database, does it query successfully? The, the serialization, does the result convert to JSON correctly? The HTTP response, does it return successfully? All these layers working together. We make a real HTTP GET request and verify we get a success status code. That is 200 OK. We also check that the response contains product in the content, confirming we got product data back. The second test is even more interesting. Create product underscore saves to database. This tests a post endpoint. We create test product data. We post it to the API as JSON. The API receives it, validates it, saves it to the database, and returns a response. We verify success. This is truly testing integration. From HTTP request to routing, to model binding, to validation, to the controller, to service, to database, and finally to the response. If any piece fails to work with the others, this test catches it. From a business standpoint, these tests give you confidence that your API actually works end-to-end. Unit tests might verify that your product service correctly processes products, but integration tests verify that a real HTTP client can successfully create and retrieve products through your API. One important note: for integration tests, you typically use a test database, but not your production database. You might use an in-memory database like SQLite or a real database in a test environment. Some teams create a fresh database before each test run and clean it up after. Integration tests take longer, maybe a few seconds each because of database operations. That's why you have fewer of them focused on critical paths, for example, user registration, order processing, or payment flows. Now we reach the top of the testing pyramid, end-to-end testing. This is testing your application exactly as a user would experience it. With a real browser, interacting with the real user interface, hitting the real backend, and using the real database. If unit tests are testing Lego bricks, and if integration tests are testing how bricks connect, then end-to-end tests are testing the complete Lego castle to see if it functions as intended. Let me give you a concrete example. Imagine you're testing an e-commerce site. An end-to-end test might open a real browser, navigate to your home page, click on a product, click on Add to Cart, navigate to the cart, click Checkout, fill in shipping information, enter payment details, and submit the order, and verify the order confirmation appears. This test touches everything: your Angular frontend, all the CSS and JavaScript, your ASP.NET Core API, your database, possibly payment gateways, email services, and more. It's testing the complete user journey. From a business perspective, end-to-end tests answer the question: does this application actually work for users? You can have perfect unit tests and perfect integration tests, but still have broken user workflows. Maybe the submit button doesn't trigger the right API call. Maybe the confirmation page doesn't display. End-to-end tests catch these issues. However, end-to-end tests have significant disadvantages. First of all, slowness. They are slow, often taking minutes or more per test because they involve for example, starting a browser, loading all page resources, HTML, CSS, scripting, images, also waiting for animations, making real network calls, and waiting for database operations. The second disadvantage is fragility. They are fragile. They break easily when you change the user interface. Did you change a button CSS class? Test breaks. Did you rename a button? Test breaks. This makes them expensive to maintain. Third, the debugging is difficult. When an end-to-end test fails, it could be any component. It could be front-end bug, it could be back-end bug, it could be database issue, it could be network problem, it could be the environment issue, or even just a timing issue where the test clicked too fast. Another disadvantage is the cost. End-to-end tests are expensive to run. You need browser infrastructure, test environments, and more computing resources. This is why end-to-end tests sit at the top of the pyramid. Only 10% of your tests, for example. You use them strategically for critical user journeys. For example, login, checkout, account creation, password reset. These flows that are absolutely must work, otherwise your business fails. Think of it this way. If your e-commerce site's checkout is broken, you lose money every minute. An end-to-end test of the complete checkout flow gives you confidence before deploying. Let's look at a concrete example using Playwright, which is a modern, powerful end-to-end testing framework that works with Angular, React, Vue, or any web application. Microsoft develops Playwright, and it's become popular because it's fast, reliable, and easy to use. Let me walk through these tests to show you what end-to-end testing actually looks like in practice. The first test is user can log in successfully. This is testing a complete login workflow. Let's go line by line. So, await page.goto opens a real browser and navigates to your login page. This loads your Angular application exactly as a user would. Next, await page.fill finds the email input field and types in an email address character by character, just like a user typing. The second fill does the same for the password field. Then we have await page.click. This finds the submit button and clicks it. It triggers your form submission, which makes an HTTP post to your backend API, which validates credentials against the database. Then we have await expect page.to have URL. After clicking login, we wait until the URL contains dashboard, meaning the user was successfully redirected after login. Finally, we verify that a welcome message appears on the dashboard. This test covers so much: your Angular login form component, form validation, HTTP request to your API, API authentication logic, database query, JWT token generation, token storage, route navigation, and dashboard rendering. If any of these pieces is broken, this test fails. The second test demonstrates adding a product to a cart. We navigate to the products page. We find the first product cart and click its Add to Cart button. This triggers Angular logic, makes an API call to your backend, updates the cart in the database. We verify the cart badge in the user interface, updates to show 1. Notice how we are using CSS selectors like product-cart, first-child, add -to-cart to find elements. This is similar to how you'd select elements with CSS or jQuery. Playwright finds elements in the actual DOM and interacts with them like a real user. From a practical standpoint, these tests are powerful but expensive. The login test might take 5 to 10 seconds to run. If you have 100 end-to-end tests, that is 8 to 16 minutes just for end-to-end tests. This is why you keep end-to-end tests focused on critical paths. Here's a tip for you. When writing end-to-end tests, think about your application from a business perspective. What are the absolute must-work flows? Login, sign up, checkout, password reset, core business features. Those are your end-to-end test candidates. Don't end-to-end test every little feature. That's what unit and integration tests are for. Another tip, end-to-end tests should be readable. Notice how these tests read almost like plain English instructions. Go to login page, fill email, fill password, click submit, verify, dashboard. This makes them serve as living documentation of how your application should work. Now let's talk about test-driven development, or TDD. This is a methodology, a way of working, rather than a specific technology. Many professional developers swear by it, so it takes practice to get comfortable with. TDD flips the traditional development process on its head. Normally, you might write code, test it manually, maybe write automated tests if you have time. TDD says, write the test before you write the code. I know this sounds backwards, but there is brilliant logic behind it. The TDD cycle is called red, green, refactor. Red phase. You write a test for functionality that doesn't exist yet. The test fails or turns red in the test runners because there is no code to make it pass. For example, you might write a test for calculate discount before you written the calculate discount method. The test will fail because the method doesn't exist yet. Green phase. Now you write the minimum code necessary to make the test pass. Not elegant code, not perfect code, just enough to turn the test green. If your test checks that calculation discount 100 0.1 returns 90, which is you make 10% discount on a price of 100 returning 90, you write just enough code to make that happen. Refactor phase. Now that you have a passing test, you can improve the code, make it cleaner, make it more efficient, make it better organized. And the test will tell you if you break anything. The test is your safety net. Then you repeat the cycle for the next piece of functionality. From a business perspective, TDD offers several advantages. Quality from start. Tests aren't an afterthought or something you add if there is time. They are built in from the beginning. This means bugs are caught immediately during development, not in production. Better design. Writing tests first forces you to think about how your code will be used before you write it. This tends to produce better APIs and more modular code. If something is hard to test, it is probably poorly designed. Documentation. The tests serve as examples of how to use your code. A new developer can read your tests to understand what the code does and how to use it. Confidence to refactor. With comprehensive tests, you can fearlessly improve and refactor code. The tests tell you immediately if you have broken something. No forgotten tests. When you write code first and test later, tests often get deprioritized and forgotten. We'll add tests later often means we will never add tests. TDD ensures tests exist for every piece of functionality. However, TDD does have a learning curve. It feels slow at first because you're writing tests before code. But many developers find that once they are comfortable with TDD, they are actually faster because they spend less time debugging and fixing bugs later. You don't have to use TDD for everything. Many teams use it for complex business logic, but not for simple CRUD operations or UI code. It's the tool in your toolkit, not a religion. If you're interested in trying TDD, start small. Pick one method you need to implement and try TDD for just that method. Write the test first, watch it fail, make it pass, refactor, see how it feels. Code coverage is a metric that tells you what percentage of your code is executed when your tests run. If you have 100 lines of code and your tests execute 80 of those lines, you have 80% code coverage. Let me show you why this matters with a business example. Imagine you've written a payment processing module. It's a critical code that handles real money. If your tests only execute 30% of that code, it means 70% of your payment logic is completely untested. That's risky. You could have bugs in that untested code that only appear in production when customers are trying to pay you. Code coverage tools analyze your code while tests run and show you exactly which lines are tested and which aren't. For C#, we use tools like Coverlet. For Angular, we use Istanbul or NYC. These tools generate reports showing coverage percentages and highlighting untested code. However, and this is crucial, code coverage is not a perfect metric. Here is why. 100% coverage doesn't mean bug-free. You can execute every line of code without testing every possible scenario. For example, a line that says if age is greater than 18 might be covered by a test with age equals to 25. But you haven't tested the boundary condition, which is age equals to 18, or negative cases such as age is 17 or minus 17. Another reason, coverage can be gamed. You could write meaningless tests that execute code but don't check anything. For example, you can write service.process order with no assertions. This increases coverage but provides no value. Another reason, not all code is equally important. 80% coverage of your critical business logic is better than 90% coverage that focuses on trivial getters and setters. So, how should you use code coverage? As a guide, not a goal. Don't aim for 100% coverage as an arbitrary target. Aim to test your important code well. Coverage helps you find what you have missed. For finding gaps, if your coverage report shows that your entire payment processing module is untested, that's a red flag. Add tests. For critical code. For mission critical code, for example, payment processing, authentication, data validation, aim for high coverage. For less critical code, lower coverage is acceptable. Recommended targets. Many teams aim for 70-80% overall coverage. This balances thoroughness with practicality. Below 70% suggests insufficient testing. Pushing for 100% usually means wasting time testing trivial code. One practical tip. Use coverage reports to focus your testing efforts. If the report shows that a critical section of code is untested, that's where you should write your next tests. Don't waste time achieving 100% coverage of trivial code while important code remains untested. From a business perspective, code coverage is a quality metric. Low coverage suggests risk, because untested code might have bugs. But high coverage alone does not guarantee quality. It's one tool among many for assessing your test suite's effectiveness. Let's talk about best practices that will help you write effective, maintainable tests. These are lessons learned from years of industry experience, and following them will save you enormous amounts of time and frustration. Test one thing per test. Each test should verify one specific behavior. Why? When a test fails, you want to immediately know what's broken. If a test checks 5 things, you have to figure out which of the 5 things failed. For example, don't write one big test called test order processing that checks order creation, validation, payment, and email. Write separate tests. Order processing with valid data, create order. And then order processing with invalid email, throws exception, etc. Use descriptive test names. Your test name should be a sentence describing what's being tested and what should happen. A bad example is test 1, test method. A good example is calculate discount underscore with 0 items underscore returns 0. When a test fails, you should understand the problem just from reading the test name. Follow the AAA pattern. We have seen this throughout. Arrange, act, assert. This structure makes tests readable and maintainable. Even experienced developers should be able to understand, even unexperienced developers should be able to understand your test in seconds. Keep tests independent. Each test should be able to run alone and in any order. Don't write test 2 that depends on test 1 running first. Why? Tests might run in parallel or in different orders. Dependencies make tests fragile and hard to debug. Use setup methods. For example, in Angular we have before each, or in XUnit we have constructors. Use setup methods to establish the state each test needs. Test edge cases and errors. Don't just test the happy path, which is what we call when everything works perfectly. Test boundaries, empty inputs, null values, negative numbers, huge numbers, invalid formats. Test error conditions. What happens when the database is down? What happens with invalid input? Business-wise, these edge cases are where bugs hide and where systems fail in productions. Now the don'ts. Don't test implementation details. Test behavior, not how it's implemented. For example, don't test that your method internally calls array.sort. Test the output is sorted. Why? If you later change the implementation to use a different sorting algorithm, your test should still pass as long as the behavior is the same. Tests that are coupled to the implementation break every time you refactor, making them expensive to maintain. Don't write dependent tests. We covered this, but it's important enough to repeat. Tests that depend on each other create debugging nightmares. When test 5 fails because test 1 didn't run, you waste time tracking down dependencies instead of fixing the actual bug. Don't ignore failing tests. This is a dangerous habit. If a test fails, either fix the code or fix the test. Don't leave it broken. Once you have one failing test, it's easy to ignore the next one, and soon your test suite is full of failures and provides no value. Broken tests are worse than no tests because they waste everyone's time. Don't test external libraries. Don't write tests to verify that Angular's HTTP client makes HTTP requests correctly or that Entity Framework saves the database correctly. Assume these well-tested libraries work. Test your code, your business logic, your use of these libraries. It saves time and focuses testing where it matters. Don't hardcode test data everywhere. If you need a test user in 20 tests, don't repeat the same user creation code 20 times. Create a helper function or use a factory pattern. This makes tests easier to maintain. When you need to change the test user structure, you change it in one place, not 20. From a practical standpoint, these best practices dramatically affect maintenance costs. Tests that follow these rules are easy to understand, easy to maintain, and actually provide value. Tests that violate these rules become a burden. Developers start avoiding them or even deleting them. Now let's talk about continuous integration, which is how professional software teams use testing in their development workflow. This is where testing really proves its business value. Continuous integration, or CI, means automatically running your tests every time someone makes a change to the codebase. Here is how it works in practice. A developer writes some code and commits it to version control, like Git. This triggers a CI server. Tools like GitHub Actions, Azure DevOps, GitLab CI, or Jenkins. The CI server automatically checks out the latest code, builds the application, runs all the tests, and reports the results. If all tests pass, the code can proceed to deployment. If any test fails, deployment is blocked and the developer is notified immediately. From a business perspective, this is incredibly valuable. Let me give you a real scenario. Without CI, a developer changes some code on Friday afternoon and pushes it. They manually test the feature they changed, and it works. They go home. On Monday morning, customers start complaining that the checkout process is broken. You investigate and discover that the Friday change broke something else. You spent Monday morning in crisis mode fixing the bug, losing revenue the entire time, and damaging customer trust. With CI, the same developer pushes the change, and within minutes the CI server runs all tests and discovers that the change broke an integration test for the checkout process. The developer is immediately notified via email or Slack. They fix the bug before they leave for the weekend. Customers never experience the problem. Crisis averted. This is the power of CI, catching problems immediately when they are cheap to fix before they reach customers. CI provides several specific benefits. Catches integration problems early. When multiple developers are working simultaneously, their changes might conflict or break each other's code. CI catches this within minutes, not days later. Ensures tests are actually run. Without CI, developers might forget to run tests or skip them when rushing. CI runs every test every time, no exceptions. Automated quality gate. CI serves as an automated quality checkpoint. No code reaches production without passing all tests. This enforces quality standards consistently. Fast feedback. Developers get feedback within minutes, not hours or days. The faster you find a bug, the easier it is to fix because the code is still fresh in your mind. Confidence to deploy. With a green CI build, which means all tests are passing, you can deploy with confidence. You know the code works because hundreds or thousands of automated tests just verified it. Documentation of build status. CI provides a history of builds and test results. You can see when problems were introduced, who made the change, and what broke. From a practical standpoint, setting up CI is easier than ever. GitHub Actions, for example, can be configured with a simple YAML file in your repository. You describe what to do, for example, build the app, run the tests, and then it happens automatically on every commit. For your projects, I recommend setting up CI even if it's just running unit tests. Start simple. Just run your unit tests on every commit. As you get comfortable, add integration tests, then end-to-end tests. The peace of mind is really worth the setup time. Let's bring this all together with a practical testing strategy for your course projects. You're building full-stack applications with ASP.NET Core and Angular, and I want to give you a realistic, achievable approach to testing given your time constraints and learning goals. Priority 1. Start with unit tests. This should be your foundation. Why start here? Because they are the easiest to learn and write, they are fast, you get immediate feedback, they catch the most bugs per time invested, and they teach you good coding habits. For your C# backend, focus unit tests on business logic methods. It can be calculations, validations, data transformations. Service classes, where you have complex logic, utility classes, and helpers. For your Angular frontend, focus unit tests on services that contain business logic, calculations, and data transformations, and state management logic. Don't waste time unit testing simple getters and setters, data transfer objects, trivial code with no logic. Each test should take 5 to 10 minutes to write once you are comfortable. Priority 2. Add integration tests. Once you are comfortable with unit tests, add integration tests for critical API endpoints. That's test that your most important API endpoints work end-to-end. For an e-commerce project, for example, test creating a product, retrieving a product, creating an order, and user registration. Database operations. Test that your data access actually works with a real database. Authentication. If you implemented authentication, write integration tests verifying that login works, tokens are issued correctly, and protected endpoints actually check authentication. Aim for a few integration tests covering your most critical operations. These give you confidence that your API actually works, not just in theory, but also in practice. Priority 3. End-to-end tests. End-to-end tests are valuable but time-intensive. If you are running short on time, you can skip these and still have a well-tested application with unit and integration tests. If you do add end-to-end tests, focus on 2-3 critical user journeys. It can be user login, navigating to main page, performing core actions, completing workflow of your main feature. For example, if you're building a task management app, it can be login and then creating a task and marking it complete. Or it can be login and view task list and delete a task. Don't try to test everything end to end. Just verify your main workflows actually work from the user perspective. Now let's have some reality check. Testing takes time to learn. Don't expect perfection. Your first tests will be slow to write and probably not great. That's normal. Every developer's early tests are awkward. With practice, you'll get faster and write better tests. From a business perspective, even limited testing is infinitely better than no testing. If your project has 30 unit tests and 10 integration tests, you're ahead of many professional projects. You've learned the skills and mindset that employers value. Let's talk about mistakes that developers make when testing, especially when they are learning. Being aware of these pitfalls will help you avoid wasting time and frustration. Pitfall 1. Brittle tests. Brittle tests break frequently for the wrong reasons. They fail even when functionality is correct. This usually happens when tests are too tightly coupled to the implementation. Bad example. Testing that a method internally creates a specific object or calls methods in a specific order. If you refactor the code to work differently but still with the same result, these tests break even though functionality is correct. Good example. Testing that given input X, you get output Y. You don't care how the code produces Y. You just care about it does. The business impact is brittle tests become a maintenance burden. Developers start ignoring or deleting them instead of fixing them. This wastes the investment you made in creating them. Pitfall number 2. Not running tests regularly. Some developers write tests but rarely run them. They might run them manually once a week or only before major deployments. The problem: tests only catch bugs if you run them. If you write code all week and run tests on Friday, you have lost the benefit of immediate feedback. When tests fail, you have to figure out which of your 50 changes this week caused the problem. The solution? Run tests constantly. After every significant change, run your unit tests. They are fast. Set up CI to run all tests on every commit. Make running tests a habit, like saving your work. Business impact. Tests that aren't run are worthless. They provide no protection and waste the time spent writing them. Pitfall 3. Testing everything. New testers sometimes try to achieve 100% coverage by testing everything, including trivial code. Example: testing that a property getter returns the property value. This provides no value. It's testing the language, not your logic. Better focus tests on complex logic, business rules, calculations, algorithms, error handling. Code where bugs can hide. Don't test simple data structures or framework code. Excuse me. Business impact. Time is limited. Hours spent testing trivial code means less time for valuable tests or features. Focus on the highest return on investment. Pitfall 4. Ignoring test maintenance. Tests need maintenance just like production code. When requirements change, tests need updating. When you refactor code, tests might need updating too. Some developers ignore failing tests or comment them out instead of fixing them. This is dangerous. You're losing your safety net. Example: a requirement changes. Discounts now apply before tax instead of after. Your tests verify the old behavior and fail. You must update them to verify the new behavior. Business impact. Unmaintained tests become worthless. They don't reflect current requirements, so passing tests don't mean the system works correctly. Pitfall 5. Not testing error cases. Developers often test happy paths, but forget error cases. What happens with invalid input? What if the database is down? What if the API returns an error? Example: testing that your order processing works with valid orders, but not testing what happens with negative prices, duplicate orders, or payment failures. The business impact is error cases are where systems fail in production. A system that works perfectly 99% of the time but crashes on edge cases still provides a poor user experience. The key lesson: testing is a skill that improves with practice. Everyone makes these mistakes initially. Be aware of them, learn from them, and your tests will get better. Professional developers still make these mistakes occasionally. The goal is to recognize them and correct course. Let's review the ecosystem of testing tools that you can use. Don't be overwhelmed by the number of tools. Each has a specific purpose, and once you understand the basics, they are all quite similar. For C# and ASP.NET Core, XUnit is a good testing framework. It provides the structure for writing tests. The fact attribute, assert methods, test discovery, and test running. It's free, open source, and used widely in the .NET community. There are of course alternatives such as NUnit and MS-Test. Mock is your mocking library. When you need to replace dependencies with fakes, like replacing a real database with a mock, it makes this easy. You saw the examples earlier. It's among the popular mocking libraries for .NET. Coverlet measures code coverage. It integrates with your test runner and produces reports showing what percentage of your code is tested. Visual Studio has built-in coverage tools too, but Coverlet works across platforms and integrates well with CI/CD. Fluent assertions is optional, but nice. It provides more readable assertions. Instead of assert.equal in parentheses expected actual, you can write actual.should.be expected. It reads more like English. Not required, but developers prefer it. For Angular, Jasmine is your testing framework. It's the standard for Angular testing and comes pre-configured when you create an Angular project. It provides the describe, it, expect syntax you saw earlier. Karma is the test runner. It launches browsers, runs your tests in them, and reports results. When you run ng-test, Karma is what's actually running. It can run tests in Chrome, Firefox, Safari, etc. For end-to-end testing, Angular historically used Protractor, but it's been deprecated. Modern choices are Playwright, which I showed you, or Cypress. Both are excellent. Playwright is powerful and supports multiple browsers. Cypress is also developer-friendly with a great user interface. Istanbul, also NYC, measures code coverage for JavaScript, TypeScript. It's built into Angular's testing setup. When you run tests, you can generate coverage reports. For CI/CD, GitHub Actions is excellent if you are using GitHub. You can set up automated testing with a simple configuration file. Every time you push code, it runs your tests automatically. Azure DevOps is Microsoft's alternative, with more enterprise features. If you are building on the Microsoft stack, it integrates well with ASP.NET Core and Azure Cloud Services. Both can run your C# tests, your Angular tests, and even your end-to-end tests automatically on every commit. Here's some practical advice. You don't need to learn all these tools deeply. You need to know how to run tests. Usually a single command. You need to know how to write tests, which we already covered. And you need to know how to read the test results, which the tools tells you what passed or failed. The tools handle the complexity behind the scenes. Focus on writing good tests. The tools will support you. Again, I recommend starting simple, using XUnit for C# testing, using Jasmine Karma for Angular testing, and adding mock when you need mocking. Also setting up GitHub Actions for CI if you are comfortable. Don't try to use every tool immediately. Start with the basics, get comfortable, then gradually add more tools as you need them. Let's address some common questions that students frequently ask about testing. I want to make sure you leave today with practical guidance you can apply immediately. How much time should I spend testing versus coding? This is one of the most common questions, and the honest answer is it depends on your experience level and the project phase. When you are learning, testing might take, let's say, 50% or more of your coding time because you are learning two things simultaneously: how to write the feature and how to test it. That's okay. It's an investment in learning. As you gain experience, testing typically takes 20 to 30% of development time. Some developers find that TDD, or writing tests first, actually saves time because they spend less time debugging. From a business perspective, the time spent testing is insurance. Yes, you could ship faster without tests, but you'll spend that saved time and more for fixing bugs later. Testing time is an investment that pays back in reduced debugging and maintenance. What should I test first in my project? Excellent question. Here's a priority list. Priority 1. Test your core business logic, such as unique calculations, rules, and algorithms that are specific to your application. If you are building a loan calculator, test the calculation logic. If you are building a booking system, test availability checking logic. Priority 2. Test critical paths. The functionality that your application absolutely needs to work. It can be user authentication, payment processing, data persistence, etc. Priority 3. Test complex methods. Anything with multiple branches, loops, or conditions. This may be where the bugs hide. Don't prioritize the things that we mentioned before, such as simple getters, setters, straightforward CRUD operations without business logic, etc. Start where the risk is highest and the value is greatest. Ask yourself, if this breaks in production, how bad will it be? Test those things first. How do I know if I have enough tests? There's no magic number, but here are some indicators. You probably have enough tests if your code coverage is 70 to 80% for business logic. If all critical paths have tests. If complex methods have tests covering main scenarios and edge cases. You probably need more tests if you are afraid to refactor code because you might break something. If you discover bugs during manual testing, that test should have code. And if important business logic is untested. Remember, quality over quantity. 30 well-written, meaningful tests are always better than 100 tests that just check trivial code. What if I don't have time to write tests? This is the most honest question because time constraints are real, especially in academic settings with deadlines. Here is my pragmatic advice. Option 1. Minimum viable testing. Write just a few tests covering your most critical business logic. This can take maybe 2-3 hours but will provide significant value and demonstrate you understand testing concepts. Option 2. Strategic testing. Identify your 3 most critical features and write comprehensive tests. For example, unit plus integration test for just those. Option 3. Test as you go. Instead of adding testing at the end, write 2-3 tests each time you implement a feature. This spreads the work and never feels overwhelming. From a learning perspective, writing even a few tests is infinitely more valuable than writing none. You will learn the concepts, tools, and mindset. That's more important than comprehensive coverage in a course project. From a business perspective, no time for testing argument is short-sighted. The time you save skipping tests, you'll spend debugging and fixing bugs. Plus, in professional settings, tests aren't optional, they are expected. Some final thoughts. Testing is a journey, not a destination. You won't master it this week or even this semester. But if you start now, practice consistently and build the habit, you'll be far ahead of most developers. The developers who write tests are the developers who build systems that don't break easily, who can sleep soundly after deployments, and who other developers want to work with. It's a skill that distinguishes good developers from great ones. Thank you all for your attention. So now go write some tests. Start small, be patient with yourself, and remember, every expert was once a beginner who didn't give up. We are starting with adding unit tests to our backend. To be able to do that, first we need to create a test project that we will call course admin system.tests. We do it by this command, that's the .NET new xunit command, and we have the -n to give the name of the project. After that, we need to add a reference to the API project. This is a rather long command. We need to type .NET add and then the project file with its path. Here it's course admin system tests. After that we say reference and then we are referring to the API project file. This is followed by the installation of the packages, for example xunit packages. We first change directory to the newly created tests project, and then in there we type .NET add package, and we will do that 3 or 4 times. So the first package is Microsoft.NET Test SDK. And then we are using xunit, so we also need to install the package of xunit. And we also need the runner, Visual Studio Runner for xunit. And the last package is we need to install the mock package for mocking. When it is all done, now we are going up again in the directory structure, and there we are adding the test project to the solution. We do that by the .NET sln add command. That's great. We need to do one more thing. Now we go to the project file. Inside the project file of the test project, at the bottom you should see this project reference. We have one reference which we created in the terminal just a few seconds ago. Here we easily add another reference, so this time we add a reference to the model project. We save the file and then we are good to go. Now the business logic in student and teacher controllers would benefit from unit testing a lot because they handle important application functionality. So therefore let's just rename the unit test file as student controller tests.cs, and then we will add one unit test that's called getStudent underscore returns OK underscore when student exists. Let me explain the code a little bit. At the top we see the using statements. So for example, using system.collections.generic is providing generic collection types and then we see the usings for the code that we have written, controllers, entities, repositories. And then we have the Microsoft.ASP.NET Core.MVC, that's for testing controller responses. And then mock and XUnit. We already saw that XUnit is a popular testing framework and mock is a mocking library. So when we continue with the test class structure, we have two private read-only fields. Repo mock is a mock object that simulates the student repository without needing a real database. And then the controller is actually the actual controller being tested, which we will use the mock repository. We continue with the student controller tests. That this is a constructor. It actually runs before each test method. What it does inside the braces is it creates a new mock of student repository, passing null to its constructor, and then it also creates a new student controller instance, injecting the mock repository using repo mock.object, which gives the mocked instance. So you can consider this part as the arrange phase of the test setup, where we ensure that each test starts with fresh objects. Then we see the test method that starts with fact. Fact is an XUnit attribute, marking this as a test method that should be executed. Then we have the test method name. Remember from the theory part of the lecture. So it follows the pattern. The first part is the method being tested, so it's getStudent. And then after the underscore, it's the expected behavior, which is returns OK. After the second underscore, then that's the expected behavior. That's the condition, which is when student exists. So, in other words, getStudent methods in the condition of when student exists should return OK. Then we move on to the body of the test method. Here we create a student object with id equal to 1, and First name is John and last name is Doe. And then on the next line, we configure the mock repository. So when getStudentById1 is called, it should return the student object that we created above. Then we have the result line. It's actually act part. It's the execute the method being tested. So we call the controller's getStudent method with id1 and store the result. And the last line is the assert part, so where we are verifying the outcome. We verify that the result is of type OK object result, which represent an HTTP 200 OK response with a body. This confirms that the controller returned successfully when the student exists. Now I want to run this test in the terminal. We can do that by typing .NET test. And let's see what will happen. And I can already tell you that the test should fail, and it did, so we have one failing test. Now the reason for the failing test is that because our student repository is not mockable. We can easily fix it by adding virtual keyword to the methods in student repository.cs. So let's just do that. After that, we will rerun the test. We only have one test at the moment. So let's just type .NET test again. There we go, the test passed. So now we have a actually test which works. Now I will add a few more unit tests. So the first addition is getStudent returns not found when student does not exist. As you can see, this is the opposite scenario from the first unit test. Let's break it down in detail. So again, we start with the arrange part of AAA. We configure the mock behavior. We have the repo mock, and then we have this lambda expression. We specify which method to call to intercept when getStudentById with parameter as 1 is called, and then we have the return statement specifies what to return, null cast as a student type. This actually simulates the scenario where the database lookup fails to find a student with ID equals to 1, so the repository returns null. And then we have the result line, that's the act part of AAA, execute the controller method. And we have the assert part. We verify that the result is of type not found result. Below that you see our third unit test that we add. It's a method that retrieves a collection of students. GetStudents returns OK with list of students. So here we first create a test collection that is a list, a generic list that can hold student objects. Inside the list we have two student objects with IDs 1 and 2. Here we are simulating what the database would return when querying for all students. So we have the lambda expression again when the getStudents method is called. Here we don't have the parameters, you remember from the API we created. When it's plural, getStudents, it's all of them. And then again we have the result where we call the controller's getStudents method. The controller internally calls the mock repository, which returns the list of 2 students that we prepared above, and then we assert, we verify the expected outcome. So OK object result represents, as I said before, the HTTP 200 OK response. Let's add one more small unit test, and that would be for testing the post endpoint that tests the input validation. So it is post returns bad request when student is null. So when we arrange, the test data is simply null, and then we don't need any mock setup because we are testing validation that happens before the repository is called. In the act part, in the result line, the post is typically, for example, we use it to create a new student, HTTP post operation. We pass the null value instead of a valid student object, and here we simulate a bad request where no student data was provided. In the assertion, we have the bad request object results, which represents the HTTP 400 bad request with a response body. Next one we are adding is post returns OK when insert succeeds. This is actually testing what we call the happy path for creating a student via post. So when we set up the test data and mock behavior, we create a valid student object with the ID 1. This represents the input data, valid input data that should be successfully saved. And then we configure the mock repository's behavior when we have the insert student is called with the specific student object, and then it returns true to indicate success, which simulates actually a successful database insert operation where the student was added. And we execute the controller method, and this calls the post method, passing the valid student object. We assert verifying the expected outcome. The OK result, as I said before, represents the HTTP 200 OK status, and this confirms that the controller returned a success status after the insert. Next one is update student returns not found when student does not exist. So this is testing an update endpoint in the API. We test a scenario where we try to update a student that does not exist. Again, we arrange creating a new student with ID equals to 1. And then we configure the mock repository where we try to look up the student with ID 1, and then the return is null. It's cast as student type. So in the act part, we call the controller's update student method. It passes the student object with updated data. And in the assert part, we verify the expected outcome. There is not found object result, such as HTTP 404 not found response. And the last unit test that I will add for this part of hands-on, where we look at the backend, is delete student returns no content when delete succeeds. We are basically testing a delete operation for the success case. And similarly, we create a student object like before, and it represents an existing student data in the database that we will delete. We set up the mock just like before, really, and then we have a second mock setup that's for the deletion, successful deletion. When the repository's delete method is called with ID, ID being 1. So this test uses two mock setups. And then we are executing the controller method by calling the delete student. And then we are verifying the expected outcome. Assert is type no content result. That's HTTP 204 no content, and that's the standard REST response for successful delete operations. So that was the unit testing in backend. Let's look at the front end. In the front end, it's actually easier in the sense that we don't need to add anything or add packages, install new things. Everything comes out of the box, and all we need to do is after the npm install, we need to type ng test. And there we go, it just finds and executes all the tests. I say finds because we already, for each component, we have auto-generated tests. That's like a good start. Now we can see that we actually have 12 specs. Those are the spec.ts files. All of them failed actually. So now we will first try to fix our failing unit tests. We start with something super easy to fix. That's the no provider for activated route error. That's on app.specs.ts. And to fix it, we just open the file, and here we just need to import provide router from Angular router, and then we need to after the imports array, we need to add providers array and then enter the provide router. There, as you can see, one success, 11 failed. So we fixed one of the 12 failing tests. Then we move on to a little bit more complicated, but also much more common problem. No provider found for HTTP client. We have it in multiple files. In order to fix that, we will again go to the failing test files. Let's start with add-student.spec.ts. We need to make two different imports this time. The first one is called provide HTTP client, and the second one is called provide HTTP client testing. And just like how we did in the previous fix, we also need to add providers array after the imports array, this time with both of the methods. And you can see one more test is a success, so now there's 10 more remaining. We continue fixing the unit tests the same way. We have a look at in which tests we have failures, and then go to those files. So for example, edit student and teacher list. So we can copy paste the provide import, and we can actually do it for multiple files while we are at it. So now I have the video running a little bit faster to save your time, but if you look carefully, we fix one more test, so 3 success, and now another 4 success. And I do more of those fixes, and I speed up the video to be even faster. I just add the imports and the providers. Now 5 unit tests are fixed. Let's continue with services. So in services we have a slightly different fix, again the same imports for both of the student and teacher services. And then inside the testbed configure testing module, we just add the providers, we don't have the imports. And when we do that, 6 and 7 success. So now we have 5 left, and here we are fixing this type error cannot read properties of undefined reading ID. So we can fix that with a similar approach. And here, as you can see, I'm working on multiple files, so it takes a little bit longer time, even though it's again with a fast speed. What we do is we again import Angular router, provide router. We also make sure that the model is imported. So if it's a component about student, it's the student model. If it's a component about teacher, it's the teacher model that has to be imported. And then the provide router, we have to add it to the providers list where we already have provide HTTP client and HTTP client testing. And we need to do that for all the test files to be fixed. After that comes the special fix for this issue. We need to create a mock ourselves. So if it's a student component, then we will create a student mock, and if it's a teacher, then we will create a teacher mock. Just to save your time and keep things easy, it will be a very simplistic mocking. So let's see here. After the creation of the component, I'm just entering in a new line. I start filling, for example, in this case, component.student, and I'm only going to add ID and first name and last name. So I need to do the same thing for all the unit tests with the same error or failure. And then when I save, now I actually have 11 successful unit tests and only one failing. And that one is a very interesting one. That's in the app level. So, and it's about the title text. So the title text is looking for hello course admin system, which is not our title. To fix that is pretty simple. So first of all, it's looking for heading 1 in the query selector. That is not correct. And then, as I said, the text is also not correct. Now, in order to fix it, we need to look at our HTML file, app.html, and there we will see that actually it's not h1 but met toolbar. And also we need to look at our in the same file or in the running page, we see that the title is course admin system, but we couldn't fix it, and the reason is actually I by mistake also added the angle brackets. We don't need the angle brackets. When we delete them, voila, we just fix it. 12 success, so all of the tests have passed. Commonly face. This will help you recognize the risks and understand why security is so important. Then we'll look at how to secure the backend of the application using ASP.NET Core. This includes things like input validation, secure data handling, and using HTTPS. Next, we'll shift to the front end, where we'll explore how Angular helps protect against common attacks like cross-site scripting. Even though the front end is what users see, it's also a potential entry point for attackers. We'll then dive into authentication and authorization, two concepts that are often confused. You'll learn how to control who can access your application and what they're allowed to do. After that, we'll talk about securing APIs, which are the communication channels between your front end and back end. APIs are often targeted by attackers, so we need to ensure they are locked down. Finally, I'll introduce you to some tools and best practices that will help you build secure applications. And throughout this lecture, we'll keep things simple and use real-world analogies to help you understand the concepts. Let's begin by understanding why security matters. It's not just about protecting code. It's about protecting people, businesses, and reputations. First, think about trust. When users visit your application, they are trusting you with their data, names, emails, passwords, maybe even credit card numbers. If that data is compromised, you lose their trust. And once trust is lost, it's incredibly hard to regain. Second, there are legal and financial consequences. In the EU, for example, the GDPR imposes strict rules on how personal data is handled. If your app leaks user data, you could face heavy fines. In the US, big companies like Equifax and Target have paid millions in settlements after data breaches. Third, let's look at some real-world examples. As I said, in 2017, Equifax suffered a breach that exposed the personal data of 147 million people. The cause? A known vulnerability in their web application that wasn't patched. In 2018, Facebook had a breach that affected 50 million users due to a flaw in their access tokens. These aren't just technical issues, they are business disasters. As future leaders and decision makers, you need to understand that security is a business priority, not just a technical one. So as we go through today's lecture, I want you to think about how each security measure contributes to building trust, avoiding legal trouble, and protecting your users. Now let's look at the most common types of security threats that web applications face. Understanding these will help you recognize vulnerabilities in your own projects. Injection attacks, like SQL injection. These attacks occur when an attacker sends malicious data to your application, tricking it into executing unintended commands. For example, if your login form sends raw SQL to the database, an attacker could enter SQL commands and gain unauthorized access. Cross-site scripting. This happens when an attacker injects malicious scripts into your website. These scripts can steal cookies, redirect users, or manipulate the page. For example, if your app displays user comments without sanitizing them, someone could post a comment that runs JavaScript in other users' browsers. Cross-site request forgery. This is more subtle. It tricks a logged-in user into performing actions they didn't intend. For example, if you are logged into your banking app and visit a malicious site, that site could send a request to transfer money using your credentials if the app isn't protected. Broken authentication means your login system is flawed. Maybe passwords are stored in plain text, or sessions don't expire. This can allow attackers to impersonate users. Sensitive data exposure is when personal or financial data is not properly protected. This could be due to weak encryption, poor access controls, or logging sensitive data in plain text. These threats are real and they are common, but the good news is, with the right practices, you can defend against them. That's what we'll focus on next. Let's now focus on the backend. This is where your application logic lives, where data is processed, and where your database is accessed. In our case, we are using ASP.NET Core, which is a powerful and secure framework, but only if we use it correctly. First, always use HTTPS. This encrypts the data sent between the client, namely the browser, and the server. Without HTTPS, sensitive information like passwords or personal data can be intercepted by attackers. ASP.NET Core makes it easy to enforce HTTPS by redirecting all HTTP traffic to HTTPS using middleware. Second, validate all user inputs. Never assume that the data coming from the frontend is safe. For example, if a user submits a form with their name, they could instead submit malicious code. ASP.NET Core provides model validation attributes like required, string length, and regular expression to help enforce rules on incoming data. Third, avoid raw SQL queries. Writing SQL directly in your code and inserting user input into it can lead to SQL injection attacks. Instead, use Entity Framework Core, which is an Object Relational Mapper, ORM. It allows you to interact with the database using C# objects and link queries, which are automatically parameterized and much safer. Lastly, use middleware for security. Middleware in ASP.NET Core acts like a pipeline that processes every request. You can plug in components for authentication, authorization, error handling, and more. For example, you can use middleware to ensure that only authenticated users can access certain routes, or to log suspicious activity. In summary, securing the backend is about being cautious with data, using the right tools, and enforcing rules at every step of the request lifecycle. Let's dive deeper into middleware, which is a core concept in ASP.NET Core. Middleware is essentially a series of components that are executed in a pipeline for every HTTP request and response. Think of it like airport security. Each checkpoint checks something different: ID, luggage, boarding pass. Similarly, each middleware component performs a specific task. For example, authentication middleware checks if the user is logged in. Authorization middleware checks if the user has permission to access a resource. Logging middleware records details about the request, which is useful for detecting suspicious behavior. Coarse middleware controls which domains are allowed to access your API, which is important when your front-end and backend are hosted on different domains. Middleware is powerful because it allows you to enforce security policies consistently across your entire application. You can configure it globally in the startup.cs file or program.cs in newer versions of ASP.NET Core. Here's a simple example. If you want to ensure that all users are authenticated before accessing any controller, you can add the use authentication method and use authorization middleware in the correct order. This ensures that every request is checked before it reaches your business logic. Middleware also helps with error handling. you can create a custom error handling middleware that catches exception and returns a friendly error message to the user while logging the technical details for developers. So middleware is not just a technical detail. It's a strategic layer where you can enforce security, monitor activity, and handle errors gracefully. Now let's shift to the front end. This is what users interact with directly. In our case, we are using Angular, which is a modern front-end framework that includes many built-in security features. One of the most important principles is never trust user input. Just like on the backend, users can try to inject malicious content into your app. For example, someone might try to submit a comment that includes a script tag to steal other users' data. To prevent this, Angular automatically sanitizes user input when you use its binding syntax. For example, if you display a variable using double braces, Angular escapes any potentially dangerous characters, so they are shown as plain text instead of being interpreted as HTML. However, if you use inner HTML to insert content into the DOM, you bypass Angular's protections. This is dangerous because it allows raw HTML to be rendered, which could include malicious scripts. So avoid using inner HTML unless absolutely necessary, and if you must use it, sanitize the content first using Angular's DOM sanitizer service. Another best practice is to use Angular's built-in bindings and directives. For example, use src instead of setting src directly in HTML. Angular's bindings are designed to be safe by default. Finally, always keep Angular and its dependencies up to date. Security vulnerabilities are discovered all the time, and updates often include important patches. In short, Angular gives you a lot of protection out of the box, but only if you use it the right way. Stick to Angular's conventions and avoid direct DOM manipulations, and always treat user input as untrusted. This slide introduces two foundational concepts in web application security: authentication and authorization. These terms are often confused, so let's clarify them with a simple analogy. Imagine you're entering a building. Authentication is showing your ID at the front desk. It proves who you are. Authorization is the security guard checking which rooms you are allowed to enter based on your role: employee, manager, or visitor. In web applications, authentication verifies a user's identity. This usually involves logging in with a username and password. More advanced systems may use multi-factor authentication, which adds an extra layer of security, just like a code sent to your phone. Authorization, on the other hand, determines what the authenticated user is allowed to do. For example, a regular user might be able to view their profile, but only an admin can delete other users. ASP.NET Core supports role-based access control, which means you can assign roles to users and restrict access to certain parts of your application based on those roles. For example, you might have roles like admin, editor, and viewer, each with different permissions. In Angular, you can use route guards to prevent unauthorized users from navigating to certain pages. For instance, you can block access to the admin dashboard unless the user has the admin role. Together, authentication and authorization form the backbone of secure user access. Without them, anyone could access anything, which is a huge risk. ASP.NET Identity is a powerful framework built into ASP.NET Core that helps you manage users securely. It handles everything from registration and login to password recovery and role assignment. Let's break down its key features. User management. ASP.NET Identity provides a user store where you can save user details like email, username, and password. It also supports external logins like Google, Facebook, and Microsoft accounts. Password hashing. When a user creates a password, ASP.NET Identity doesn't store it as plain text. Instead, it uses a technique called hashing. Hashing converts the password into a fixed-length string that cannot be reversed. Even if someone steals the database, they won't be able to read the passwords. Role management. You can define roles and assign them to users. For example, you might create an admin role and give it access to sensitive features. ASP.NET Identity makes it easy to check a user's role and restrict access accordingly. You can also customize the identity system to include additional fields like phone number, address, or preferences. It's flexible and integrates seamlessly with ASP.NET Core's authentication and authorization middleware. JSON Web Tokens, or JWTs, are a popular way to handle authentication in modern web applications, especially when you are working with APIs. Let's start with the concept of stateless authentication. In traditional systems, the server stores session data for each user. But in stateless systems, the server doesn't store anything. It relies on tokens that the client sent with each request. A JWT is a compact, self-contained token that includes all the information needed to verify a user. It has three parts. Header specifies the algorithm used to sign the token. Payload contains the user's data, like their ID, email, and roles. Signature is a cryptographic hash that ensures the token hasn't been tampered with. When a user logs in, the server generates a JWT and sends it to the client. The client stores it, usually in local storage or in a cookie, and includes it in the header of every API request. The server then verifies the token and grants access based on its contents. JWTs are great for scalability because they don't require server-side session storage. They are also secure if implemented correctly. Always sign them with a secret key and set an expiration time. In ASP.NET Core, you can use the Microsoft.ASP.NET Core.authentication.jwt bearer package to validate JWTs. In Angular, you can use interceptors to automatically attach the token to every HTTP request. You can think of JWTs like a passport. Once issued, you carry it with you and show it at every checkpoint. The passport contains your identity and permissions, and the border agent, which is the server in this case, checks its validity before letting you through. APIs are the communication bridge between your front-end and back-end. They allow your app to send and receive data like user profiles, product listings, or form submissions. Because APIs are exposed over the internet, they are prime targets for attackers. So, securing them is absolutely critical. First, always use HTTPS for API communication. This ensures that the data exchange between the client and server is encrypted. Without HTTPS, attackers can intercept and read sensitive information like login credentials or personal data using techniques like packet sniffing. Second, validate all inputs received by your API. Even if the front-end already validates the data, never assume it's safe. Attackers can bypass the front-end and send requests directly to your API using tools like Postman or curl. Use ASP.NET Core's model validation attributes to enforce rules on incoming data. Third, authenticate every request. Don't rely on session cookies alone. Use tokens like JWTs to verify the identity of the user making the request. Every API endpoint should check whether the user is authenticated and authorized to perform the requested action. Finally, limit data exposure. Only return the data that's necessary. For example, if your API returns a list of users, don't include sensitive fields like passwords or internal IDs. Think of your API as a vault. You want to make sure only trusted people can open it, and even then, they should only see what they are allowed to see. Once you build the API, it's important to test its security, not just its functionality. This is where tools like Postman come in. Postman allows you to send HTTP requests to your API and inspect the responses. It's like a remote control for your backend. Start by testing with invalid inputs. For example, if your API expects a number, try sending a string. If it expects a short name, try sending a very long one. Your goal is to see how the API handles unexpected or malicious data. A secure API should reject invalid inputs gracefully and return appropriate error messages. Next, test for unauthorized access. Try accessing protected endpoints without a token. Then try using a token for a regular user to access admin-only features. If your API allows these actions, it's a serious vulnerability. Also, test for rate limiting. Can you send hundreds of requests in a few seconds? If so, your API might be vulnerable to denial of service attacks. Finally, check the error messages returned by your API. They should be informative but not too detailed. Avoid exposing stack traces or database errors, as these can give attackers clues about your system. Testing API security is like stress testing a bridge. You want to find the weak spots before someone else does. Errors are inevitable in any application, but how you handle them can make the difference between a secure app and a vulnerable one. First, don't expose technical details in error messages. If a user submits a bad request, show a friendly message like "something went wrong, please try again." Avoid showing stack traces, database errors, or internal file paths. These details can help attackers understand your system and find vulnerabilities. Second, log errors securely on the server. Use ASP.NET Core's built-in logging framework or third-party tools like Serilog or Nlog. Logs should include the timestamp, user ID if available, request details, and the error message. But be careful not to log sensitive data like passwords or credit card numbers. Third, monitor your logs regularly. Look for patterns that might indicate an attack, like repeated failed login attempts, unusual API usage, or requests from suspicious IP addresses. You can set up alerts to notify you when certain thresholds are crossed. Good error handling is like having airbags in a car. It doesn't prevent accidents, but it helps you recover safely and understand what went wrong. Let's talk about CORS, which stands for Cross-Origin Resource Sharing. This is a security feature built into web browsers that controls how web applications interact with resources from different domains. Here's the problem CORS solves. Imagine your Angular frontend is hosted at https://myapp.com and your ASP.NET Core backend API is hosted at https://api.myapp.com. Even though they are part of the same app, they are technically on different domains. By default, the browser blocks requests from one domain to another unless the server explicitly allows it. This is a good thing. It prevents malicious websites from making unauthorized requests to your server, but it also means you need to configure your backend to allow requests from your frontend. In ASP.NET Core, you can configure cores in the startup.cs or program.cs file. You define which origins are allowed, which HTTP methods are permitted, and whether credentials like cookies can be sent. Here's an example. After this, you apply the policy like that, which tells the server it's okay to accept requests from myapp.com. Without this, your frontend will get course errors and won't be able to communicate with the backend. Course is like a guest list at a party. You don't want just anyone walking in. You want to allow only trusted guests. Configuring course properly ensures that your API is accessible to your frontend, but protected from unauthorized domains. Protecting sensitive data is one of the most important aspects of web application security. This includes things like passwords, personal information, and authentication tokens. Let's start with encryption. Encryption is the process of converting data into a format that can't be read without a special key. For example, if you store a user's password, you should never save it as plain text. Instead, you hash it using a one-way algorithm like SHA-256 or bcrypt. ASP.NET Identity handles this automatically. Beyond passwords, you might need to encrypt other data, like email addresses, credit card numbers, or session tokens. ASP.NET Core provides a data protection API that makes this easy. It uses industry-standard algorithms to encrypt and decrypt data securely. Here's a simple use case. You want to store a token in a cookie. If you store it as plain text, someone could steal it and impersonate the user. But if you encrypt it using the Data Protection API, even if someone steals the cookie, they won't be able to read or use it. You can also use the API to protect the data in temporary storage like temp data or view data, which are used to pass information between pages. Another important area is securing cookies. Always set cookies with the secure flag so they are only sent over HTTPS. Use the HTTP-only flag to prevent JavaScript from accessing them, and the same site flag to prevent CSRF attacks. Think of encryption like a safe. Even if someone breaks into your house, which for example is your server in this case, they still need the combination, which is the key, to open the safe, which is the data. By encrypting sensitive information, you add a powerful layer of protection. Security isn't just about tools, it's about habits. Let's talk about some secure coding practices that you should follow. First, never trust user input. This is the golden rule of security. Whether it's a form field, a URL parameter, or a file to upload, always assume the data could be malicious. Validate and sanitize everything. Use built-in validation attributes in, for example, ASP.NET Core and Angular's form validators to enforce rules. Second, use parameterized queries. If you're interacting with a database, never build SQL queries by concatenating strings. This opens the door to SQL injection attacks. Instead, use entity framework or parameterize commands that separate the query logic from the data. Third, keep your dependencies updated. Your project relies on libraries and packages, like Angular modules or NuGet packages in ASP.NET Core. These packages can have vulnerabilities. Regularly check for updates and apply them. Tools like npm audit and .NET list package with the parameter --outdated can help you identify outdated or vulnerable packages. Fourth, review your code regularly. This includes manual code reviews with your team and automated static analysis tools. Look for hard-coded secrets, unused endpoints, or overly permissive access controls. Even simple mistakes like forgetting to check user roles can lead to serious vulnerabilities. Secure coding is like good hygiene. It's not flashy, but it prevents problems before they happen. By building these habits early, you'll write code that's not only functional, but also resilient and trustworthy. One of the most valuable resources in web application security is the OWASP Top 10. OWASP stands for the Open Worldwide Application Security Project. It's a non-profit organization that provides free, community-driven resources to help developers build secure software. The OWASP Top 10 is a regularly updated list of the most critical security risks to web applications. It's based on real-world data and expert consensus, making it a reliable guide for developers and security professionals. Some of the key risks include injection attacks like SQL injection, broken authentication where login systems are poorly implemented, allowing attackers to impersonate users, cross-site scripting, also sensitive data exposure and security misconfiguration. Each item in the OWASP Top 10 includes examples, impact analysis, and recommended mitigations. You can use it as a checklist when building or auditing your application. It's especially useful for students and beginners because it highlights the most common and dangerous mistakes. Think of OWASP like a health checklist for your app. Just as doctors check vital signs, developers should check for these top 10 risks to ensure their app is healthy and secure. Let's look at some practical tools and libraries that can help you implement and test security in your full-stack application. ASP.NET Core Identity. This is a built-in framework for managing users, roles, and authentication. It handles password hashing, login workflows, and role-based access control. It's secure by default and integrates seamlessly with ASP.NET Core. Angular DOM Sanitizer is a service that helps you clean up potentially dangerous HTML content before rendering it. It's especially useful when you need to display user-generated content like comments or reviews without risking cross-site scripting attacks. Postman is a powerful tool for testing APIs. You can simulate requests, test authentication, and inspect responses. It's great for verifying that your backend is secure and behaves correctly under different conditions. OWASP Z-Attack Proxy is a free security scanner that can automatically test your web applications for vulnerabilities. It simulates attacks like cross-site scripting and SQL injection and provides detailed reports. It's beginner-friendly and widely used in the industry. These tools are like your security toolkit. Just as a carpenter uses a hammer and level to build safely, developers use these tools to build secure applications. You don't need to master them all at once, but knowing they exist and how to use them will make you a more confident and capable developer. Security isn't just a checklist, it's a mindset. To build secure applications, you need to think like an attacker. Ask yourself, if I were trying to break into this app, what would I do? This helps you identify weak spots before someone else does. Be proactive, not reactive. Don't wait for a breach to start caring about security. Build it into your development process from the beginning. Use secure defaults, validate inputs, and review your code regularly. Also, remember that security is everyone's job. It's not just the responsibility of the backend developer or the IT department. Front-end developers, designers, product managers all need to understand the basics of security. For example, a designer should know not to include sensitive data in URLs, and a product manager should prioritize features that protect user privacy. In business terms, think of security as risk management. Just as companies manage financial and operational risks, they must manage digital risks. A security mindset helps you build trust, protect assets, and ensure long-term success.